The other property that is affected by the presence of a solute is the freezing point. So boiling point's affected, where that temperature is, and then the freezing point is affected, where that temperature is and where that transition occurs. So the freezing point is going to see a different trend, though. Freezing point, if you remember, is it's the temperature where solid and liquid phases are at equilibrium with each other. They're just both present at the same time. And what we're seeing at that temperature is the solid substance, which has some motion available to it. The particles are able to move and move past each other. At that temperature, if we're solidifying something, then everything gets locked in position. We remove enough energy that they all form a nice crystal solid. And what a solute does is it disrupts that crystal solid. So what we're seeing with for the liquid to solid transition, molecules are becoming regularly arranged and tightly packed. And if a solute is there, it's going to be harder to find that regular arrangement. The arrangement is going to be disrupted. A solute disrupts that arrangement. So we're going to have to remove even more energy from the liquid in order to force it into this solid arrangement. It's going to take a lower temperature to solidify a solution. Okay, to create a solid out of a solution, it's going to take an even lower temperature just to force it into that solid arrangement. And so what we say is there's a freezing point depression. The freezing point goes down to a colder temperature. And we're going to see a similar equation where we say the amount that the temperature decreases for a freezing point, the amount the freezing point decreases is equal to a constant, Kf. This is the freezing point depression constant. Freezing point depression constant, and times the molality. Molality. So this is going to tell us by how much does the temperature of a solvent, man, I get those two confused, is what I'm saying. By how much does the temperature of a solvent decrease when we add in a solute, when we add in something that we're dissolving in it? So we're going to do just one example of freezing point, because the equations and the math is really just the same with the boiling point elevation, except that we're lowering the temperature instead of increasing it. So what is the freezing point of a 1.85 molal solution of a non-volatile electrolyte solute in nitrobenzene? So what's the freezing point? So the freezing point of solution, because it's a freezing point depression, that means we're going to take the original freezing point and subtract the change in temperature of that freezing point decrease. We're going to subtract that temperature amount from the normal freezing point. And that's going to mean that the freezing point of the solution is equal to the freezing point minus this constant. For freezing point, it's a different constant than the boiling point elevation constant. It's a different number. So we take this freezing point depression constant times also the molality. So I need to find, so for nitrobenzene, that's the other thing, is we have to see what is our, what's our solvent. For nitrobenzene, the freezing point is normally, for a pure solvent, the freezing point is 5.67 degrees Celsius. So normally it would freeze at 5 degrees Celsius. And then the freezing point depression constant, which you would have to look up, is 8.1. That feels like a big number. 8.1 degrees Celsius per molal. So I'm just going to plug all of this in. I have my normal freezing point, which is 5.67 degrees Celsius, and then I subtract my freezing point depression constant times the concentration in molality, which is given in the problem here just as the right unit. And again, molality units cancel out. So I get 5.67 minus 8.1 times 1.85. I want to double check sig figs. 8.1 times 1.85 is going to get me, so it's going to be 5.67 degrees Celsius minus, and this minus I picked because it's a depression. We're lowering the temperature, so you have to have it subtracted out. Minus times 1.85. So sig figs, there'd be two significant figures on that, which would be 15 minus 15 degrees Celsius. Dang, that's a lot. And then, so that would equal 5.67 minus 15 equals negative 9.3 degrees Celsius. So the new freezing point of this nitrobenzene solution is negative 9.3. It goes from 5 degrees Celsius, which is above zero, down to negative 9.3 degrees Celsius, which is below zero. And this is the reason that you might throw salt or some solid on the frozen roadways, is because it actually would lower the temperature of the freezing point. It would require a lower temperature for the ice to freeze. And so if you're just at maybe 30 to 32 degrees Celsius, then you could sprinkle something on the roadways and that ice would melt, and eventually it would freeze at an even lower temperature, maybe overnight. But if you throw a lot on, then that would even increase the freezing point depression and make it so that the roadways aren't so icy. Okay, so that's kind of practical application for this sort of idea. The last thing that I wanted to mention is the idea of osmosis, because osmosis is something that happens with solutions as well. It's a property. Osmotic pressure is going to be a property of solutions. And so what we're looking at is Osmosis being kind of the movement of a solvent across a semi-permeable membrane. So we have, let's start with the picture. We have the picture here of some tube that has a membrane in the middle. And what the membrane does is it's permeable to some molecules. Some molecules that are small can go through it, but molecules that are large cannot. So here we have this membrane that allows solvent molecules through, where we have pure solvent on this side, but it doesn't allow the solute particles back through. Okay. So it's kind of a one-way, or one type of particle is allowed to flow across this membrane. And osmosis is the flow of the pure solvent into the side where there's a solution, because we have a lower concentration. Here, with the solution, we have a lower solvent concentration. Here, we have a higher solvent concentration because it's pure, 100% concentration, right? And osmosis is the flow of the pure solvent across this membrane into the portion with the lower concentration, and it flows that way because of the difference in concentrations. It's trying to find this equilibrium where maybe the concentrations are equal, but at some point it kind of stops the flow. And what stops the flow of the pure solvent in, right? We don't get all of this rushing in. The reason that not all of these particles go across is because at some point after we've had some flow, the liquid level gets higher. So as solvent flows through the membrane, we get an increase in the volume, right? This is the increase in the volume, the difference in the volume. And there's actually a pressure associated with that height of liquid. The weight in that column gets high enough, and the pressure gets high enough that it starts to actually force some solvent back through the other way. So initially, we have some separation here, and the levels are equal. So solvent goes through to try to dilute that solution. But eventually, the liquid level gets so high that there's a pressure pushing some particles back through. And the osmotic pressure is the pressure where we've reached an equilibrium, where there's enough pressure that the particles are still going through, but there's an equal number going back that's kind of equalized the flow of solvent, and we don't have more solvent continuing to flood the solution. So we have this osmotic pressure that's the pressure that will kind of stop the osmosis, stop the one-way flow of solvent into the solution. And osmosis, I'll give you guys a definition for it too, just so that we can move forward with that. But osmosis, I was looking it up, is diffusion driven. So we get the flow of solvent across this membrane, diffusion-driven transfer of solvent molecules through a semi-permeable membrane the flow of solvent molecules through a semi-permeable membrane. And the reason that we get the flow is possible, but because we have a solution on the other side, we actually get a pull of pure solvent through it in order to dilute that solution more. And that happens spontaneously until the pressure gets too high for it to continue to build up on just one side. A biological application of this, or consideration, if we look at red blood cells, when you're injected with solutions, they need to be the same concentration as our blood cells are. So we have water plus other things. And so if we have a greater concentration of water in the solution that you're injecting, then you're going to get some problems with some of your cells. And so I wanted to just look at that. If you have, so we have the middle picture I'm going to start with. The desired solution will have equal concentration. So if the osmotic pressure is equal to of the solution is equal to the osmotic pressure of the blood cells, the blood serum, maybe it's not quite the cell, then we end up with an isotonic solution. We want the solution that you're injecting to be isotonic with the blood serum so that we don't get some unequal flow of water. If we have the osmotic pressures are equal, then the flow of water into the cell is going to be equal to the flow of water out. The rates will be the same so that we don't get extra water coming out of the cell or extra water going into the cell. And that's when we get some problems, is when the osmotic pressures are not equal. Osmotic pressure being the pressure exerted by the liquid. If we have a case where more water is flowing into the cell, right, than out, if we have like a less concentrated solution outside the cell, right, that'd be like up here. If we have a less concentrated solution here, the solvent is going to flow into the cell at a rate that is too high, okay? And you actually get more and more and more and more water, and the blood cell can burst. It'll expand and rupture, hemolysis. So this is where the solution concentration, or the solvent, less concentrated solution than blood serum concentration. Okay, we have more solvent outside the cell than inside, and so we get the flow of that solvent into the cell, and we get hemolysis. This is a hypotonic solution. Less concentrated, hypotonic solution, and the effect is going to be bursting of the cells, hemolysis. Okay. Hypotonic is less concentrated, and so the osmosis, we see osmosis from the less concentrated to the more concentrated to try to dilute that solution that's inside the blood cell. And then the reverse would be if we have a hypertonic, a more concentrated solution outside. Hypertonic, this is going to be more concentrated solution injected than blood serum. And in that case, right, if we have a more concentrated solution out here, then you're actually going to get water going out of the cell at a higher rate because it's trying to dilute what's outside the body with the water. And we're not getting very much put back in. And so these cells actually shrivel up because the water is being sucked out of them. These cells will shrivel up, and the effect is called crenation. They may die. Okay. So the concentrations of solutions that are injected into your body, or if you're going to be a nurse, into someone else's body, need to be the same concentration as the blood serum. Otherwise, you can do damage to the blood cells caused by this osmosis process. Okay. So that's it for chapter 11. Exam 4 is just going to be chapter 10, 11, and 12. 10 you've already viewed and studied, so keep studying that one. Chapter 11 we're just finished covering now, and then I'm going to post a video or two about chapter 12, and then that's going to kind of cover the information for that last midterm exam before the final. I will see you guys in the videos where we talk about chapter 12.